So I wanted to show this section E, or at least some of the problems in section E, because I think these are a really important collection of field extensions and splitting fields that somehow we've managed to make it this far without talking about. These deal with roots of unity, and the fields denoted Q omega in Pinter. I'm going to stick an N down here just for clarity because sometimes and in some contexts you have multiple different roots of unity running around at the same time. It's helpful to know which one is which, so that's just a little habit of mine. But omega n is a root of x to the n minus 1, which is not 1. Because, of course, if you plug 1 into here, you get 0. But we're interested in somehow the non-trivial roots of unity. So like minus 1 for degree 2 and complex roots in general. And so there's a typo or two in this section also. I thought it might be helpful to just show some stuff about these objects rather than, try to go and correct the typos and then I have to solve all the problems myself, and that just seems like it would chew up a little bit of time. So in any case, um, as I said, these omegas satisfy a simple polynomial. Um, the first thing that I want to point out about them is that they have a exponential, a complex exponential formula, where I here is the imaginary number. And with this picture in mind, exponent rules say that this is the if you raise this to the nth power, that's the same thing as e to the 2 pi I. And it turns out this is a fact that you have to just know, or if you don't know it, you will know it soon because soon TM. When we talk about complex analysis in however many months or so, I will explain this to you. But the exponential function is actually 2 pi I periodic. And so e to the 2 pi I is the same thing as e to the 0 or 1. And so what this means is a simple consequence, if you know this, I mean, it's not too much harder to prove if you don't, but we'll use it. The omegas, omega n to the power of I, this set, form a cyclic group, isomorphic to z mod nz, right? Where basically, I don't know what else to say, right? If the nth one of these things is 1, then the powers 1 through, or 0 through n minus 1, 0 being the same thing as n, are n complex numbers, and they multiply according to multiplication rules. So this is sort of straightforward. However, this ends up being more than a little bit useful because, for example, um, if you have a field that contains one of these omega n's, it contains them all. Well, I should be clear. If you contain a generator for this group, it contains them all, right? If n is equal to 4 and you have the fourth root squared, right? Then you only have 2 and 4. So oftentimes omega to the n, or sorry, omega sub n is used to mean a principal generator, principal root of unity, like this guy, right? This is a principal root of unity. So I'll say contains omega n, a principal root of unity, or omega ni for I coprime to n. Right, that would do the same thing. Then K contains all the roots of unity. And that's very helpful because one of the facts that Pinter asks us to prove is that Q adjoined this omega n is the splitting field, the root field of x to the n minus 1 over Q. And what we're basically being asked to prove here is that all the roots of x to the n minus 1 are contained in this thing once you have one of them. And that's kind of what we've said here. Basically, the thing to see is that if I can factor x to the n minus 1 completely in some field extension, I write this as a product, maybe like so. maybe like this, for example. And because each of these things can be generated from the others once you have a principal root of unity, you have them all. I had one other thought in my head I wanted to share about this. Where did it go? What did I want to say? Oh yeah, I remember. Which is that this polynomial actually factorizes. Like this is not an irreducible polynomial. At least certainly not always. X to the n minus 1 over x minus 1 has this very simple form like so. And this probably warrants some explaining, and maybe even a brief proof. Proof is very simple. It's kind of just algebra. Multiply both sides by x minus 1. Right? These evidently cancel. Over here, when I do x into all of this, I get sum I equals 1 to n of x to the I minus the original thing itself, which is I equals 0 to n minus 1. And then what you see is these things have a high degree of overlap, right? Everything in here is also in here, except the nth term, and vice versa, except for the 0th term. So this is x to the n minus 1, which is what we wanted. And so the relevance is that this x minus 1, in some sense, we know that this something like this has to be the case because Q contains 1 already, right? And in fact, any field contains a 1, sort of by definition. And so all of these non-trivial things, right? These are where these non-trivial roots of unity come from, right? The other n minus 1 nth roots of unity that one may seek. Okay, and then there's maybe one last part that I want to talk about for this, um, or maybe more than one last part, maybe even two parts. The first thing I want to say is that a similar story works if you replace the polynomial x to the n minus 1 with x to the n minus a. So in other words, if I look at roots of this thing and I want to know what is the splitting field of this guy, um, we can do something similar, right? I can set this equal to 0 and then try to write x as the nth root of a. But I have to be a bit careful because when I'm taking these nth roots, right, we know that a is equal to a times 1. And so it will so happen then that you will have not just one nth root of a. That doesn't really make any sense, right? This is a little bit suspicious, right? There are n roots of a, right, in a splitting field because they're all distinct. And so in that situation, then you have this thing, which you might think of like as a simple real or complex number, a principal root. But in order to get a full splitting field, I need to remember the roots of unity are also possible so that I have n distinct roots. And so what we have to do is look at Q, adjoin this nth root of A, and then we also have to adjoin this omega n. And I think I'm going to leave to you guys the relatively simple verification that this is in fact the splitting field. Okay, there's one last thing that I wanted to talk about in this section, which is that these polynomials play an important role in the theory of field extensions. They come up in number theory quite a bit. However, it is not always the case. And let's see, I think Pinter says something about this too. Yeah, so he says if n is prime, here's what's in Pinter. If n is prime, then omega to the n minus 1 is a linear combination of the lower powers with rational coefficients, which leaves us to wonder what could happen if n is composite. And then in particular, he gives us a sort of follow-up question, which is to calculate the degree of q omega n over q when n is 6, 7, 8. And I think this is a worthwhile exercise. And so I don't want to spoil it too much. The simplest thing to do is to just try to collect all of these roots of unity and then multiply them out for yourself. I mean, of course, one of them here is prime, so we know what's going on here. But for 6 and 8, what I recommend doing, so this is a little bit of a hint, is to go look up, if you don't already know, de Moivre's formula. In particular, this formula is related to the thing that I wrote at the beginning with the Euler formula. Euler formula says that for any real number theta, e to the I theta can be written as cosine theta plus I sine theta. And this is a really beautiful and critical fact for dealing with complex numbers. And de Moivre's formula is sort of saying that this is, well, okay, it's an instantiation of this. De Moivre did not know the Euler formula. But so what he was realizing is that you can calculate multiple angles with an exponential type formula, and that's correct. And so you might use this to analyze these roots of unity, since every root of unity is of this form. Okay, I think I'm gonna leave that here. At this point, I feel like I've been talking too long, as always. But hopefully, after one takes a crack at this, one has started to feel that root fields are not so mysterious and scary. Of course, if you have any questions, write to me on the discussion board and we'll talk soon. Take care.